So Adam Steger is an entrepreneur and engineering leader focused on applying robotics to solve large-scale challenges to replace chemical pesticides. Trick Robotics, he's CEO of Trick Robotics, which replaces chemical pesticides with automation, deploying fleets of autonomous robots that use ultraviolet light and integrated tools to manage pests and disease in specialty crops. Trick has expanded from pilot projects to commercial deployments across thousands of acres, backed by leading venture investors to accelerate growth. So thanks so much, Adam. Take it away.
Man, I could not do a better intro of myself, so thank you. Thanks a lot. Thanks a lot for the intro. As you said, Adam Steger, founder and CEO here at Trick Robotics, and we've been helping farmers control pest and disease using ultraviolet light as a replacement for chemical pesticides. Here you can see a couple of our robots in the field to get a feel for what that looks like. But we're in a really unique position that we just came out from taking this technology from the garage out and scaled it to commercial applications. But because we're not so far on the commercial track yet, we have a lot of learnings that we could share with all of you that hopefully can help some of you guys get from prototype to profitability, because that should be the goal of all of us. And I shared this picture because we also were a prototype not long ago. This is my co-founder and I in the field with our first ever robot. We had just learned about this UV technology, and it had spent 10 years in the lab. After talking to some farmers, we found that in specialty crops particularly, they were really struggling to control pest and disease. And this was because of the resistance to the chemical and also a lot of pressure on the regulatory side. So as gung-ho founders, we were super excited to get into our first market. We decided to focus on strawberries because more chemicals were used there than any other fruit or vegetable. The only challenge was we were in Delaware and it was 2,500 miles away and 90% of the market was in California. So we did the founder thing and drove across the country and came out here. We got 2 farmers to agree to half-acre pilots. So some of you guys might be at that stage now. We were super excited about that then, and it's kind of funny looking back because now the robots that we have can do almost 100 acres each. And this is what our robots look like now. This is not CGI. It just looks like the future because it is the future. This is a 25,000-pound machine. We call it Luna. We've got 12 of them running around in Santa Maria and Oxnard, California, 2 of the big growing regions for strawberries. And we provide the light as a service that replaces the chemical cost for the farmer. So it's a budget item in their existing budget. So we provide it as a service because they do sprays today as a service. So we try to make this fit in their operations as easily as possible. And one of the unique things about the light, this picture is at dusk, so you can see the robot a little better, but we actually run this at night. And that's one of the key aspects of the technology that scientists learned. And it turns out that that's also really great for adoption. So all these little wedges to market really helped us drive quick adoption of this technology. And I think one of the most important things that we did early on was not focus on the robot. My background is in robotics, so it was really tempting. I really was excited to build cool robots. But every time I went to talk to farmers about what we were doing, I told them, hey, this technology that's been in the lab for 10 years, we're excited to bring it out to the world, and we're going to build this really cool robot that's going to do that. And every time they were like, I don't care about the robot. Like, tell me more about the light. What I care about is this amazing result that I've seen in the lab for umpteen presentations at this point. I want the strawberries that don't have the fungus on them. By happenstance, we talked to the right farmers that pushed us in the direction away from the robot and into the light. And I think there's a lot of technologies like this in labs that can be brought out into the world. And what we found after talking to the scientists was the key thing here was the dose. And it's really hard to get the right dose in the field compared to in the lab. So what they were doing in the lab is they'd flick the light switch on, and then really quickly they'd turn it off, and then you'd get the dose. And you had a really nice controlled condition. But some of these technologies like this one, when you start bringing it out to the field, there's a lot of challenges. How bright is the light? How much is it affected by the environment? How close do you need to be to the plants? Are you getting good penetration and coverage into the canopy? These were the real tech stack that we needed to solve, not just the automation. So you can see in this picture here what that looks like. If you just haphazardly carry these lights around through the field, what you end up with so much variability that you end up not treating some of the plants, and then you end up overdosing some of the other plants. So without focusing on the right tech stack, we could have accidentally drove around in the field and provided no value to the customer and killed a technology that can replace as much as 75% of the chemicals that we're using in these strawberry fields. So if you're looking for the right tech stack, make sure you focus in the right place. Now, I'm also a huge fan of launching unfinished solutions. So get in the field as quickly as you can. This is something that we did right away once we had the array. So we focused on the dose and the light, and then we said, okay, we need the minimum viable thing to carry this around in the field. And it ended up being just a couple motors, an encoder, and a couple GPS units. And that was basically a couple $1,000s that helped us get the technology out to the farmer. And the important thing here was we did it really quickly. We focused on trying to make sure that we can learn as fast as possible instead of build in the lab something like really perfect. And there's some really incredible examples, I think, here at the bottom. We've got the robots were so small that they were constantly getting stuck, but that was actually a really good thing because now that our robots are so big, if we take a left turn in the middle of the field, we end up destroying like half of the strawberry field. Back then, we were taking left turns all the time by mistake. And it was okay, because the robot would get stuck, we'd go over, we'd push it out. So it was unscalable, but it was the right way to get started. And because we went to market really quickly, we were able to make these mistakes and still build that relationship with the customer. We also, these are things that probably some of you guys are doing if you're using GPS, because GPS was the way that we found was much better than using camera systems to navigate. Camera systems would take a lot more time to get in the field, so we said, okay, let's use GPS. And we went out there and we tagged all the GPS points that the robot was going to follow. Totally not scalable, but it meant that we didn't have to hire software engineers and we didn't have to kind of build this big team with a lot of burn. And this was only half-acre plot, so we were able to get out there really quickly and get this robot running around to show that value to the customer, because that's the most important thing that you're trying to do at this stage. And this, just to show this picture again of Vishnu and I, another thing that I think is really key is for the founding team to really be out there in the field with the technology, because probably all the really interesting nuggets of information that we've learned that got us where we are today came from that late night that we were out there in the field and the farmer swang by in his pickup truck and said, hey, how's it going? And then we got to talking to them, and they shared some insights that ended up teaching us what we needed to do to really scale this business up. So I think being in the dirt, if you're in the lab, you're not going to learn those things. So I think it's just so critical if you're building a company in ag to just get out there and be on the farm with these farmers. You're going to learn way more by doing that, even if the solution looks like just a couple pieces of metal with tires. It's better to do that than put all the fancy covers on it. And once you have, I should probably say this last bullet, so important. It probably should be the first bullet, honestly. If you're going to get into any new technology on a farm, you really need to just at least grab a napkin and sketch some of the numbers out. When we're talking about UV, some people ask me sometimes, couldn't you just use a drone to do that? And if you just run the numbers, within 5 minutes, you're going to see the drone has to be gigantic because the amount of power and fuel you'd have to carry to power the lights. It's not something that you could even practically take to the farm. So I think sometimes technologists, like myself, being a roboticist, may go down paths that are ultimately never going to be a business. And the worst thing you can do for yourself is waste time, because you can get money back, but time is something you're not going to get back. So make sure you're just focused on a problem that could actually pan out to be a real business. And if you are convinced that you've got a great problem and it can be a great business, the next thing you have to do, and what we did, was convince the farmers that it works. And for us, it was UV light in the field. And we actually did this wrong to start. We started talking to the farmers, how can we validate this technology for you? And they said, well, if there's less mites on the leaf with the UV light than with the chemicals, then we agree that it works. And I think that was a good step, because then we said, well, okay, if you agree that it works and we get that result, can we scale up next season? So we did still follow that path. But one thing that we did wrong is, and I learned this from the Western growers case studies, they're amazing, by the way, you relate that as close to profitability as you can. I think as close as you can relate your value to the profitability of the farmer, If you can do that really well, then you're going to get adoption way, way faster. So make sure you understand the problem up to that level. Don't take the scientific approach and count mites on leaflets. If you stop there, it's going to be a lot harder to drive adoption. But you are going to get a lot of really good plots, and I think these are also valuable. And the best way to get these is to partner with third parties. I think one really amazing thing in ag is we have this extension from university, and these scientists are trusted third parties that the farmers go to. So if you're validating a new technology in the market, it's really key that you find the right people that can help get your message and basically the result that you're validating in the field out to these people. And they're going to stand up on stage like this, and they're going to talk to a bunch of farmers. And because they're the trusted third party, it's going to really open up a lot of doors that you wouldn't otherwise have been able to do if you collected the data yourself. So really key, I think you can follow the data. One thing that we learned along the way, we actually were running the lights, and we didn't know enough about strawberries. So as the strawberry plants grew, they got too close to the lights, and they started blocking the light from the rest of the plant. And because we were working so close with these third parties, we saw a blip in the data. We were like, oh no, our mite levels are going up. What are we doing wrong? And if we weren't really keeping our eye on the data, then we wouldn't have been able to see this. I mean, this isn't true for every type of technology, but in our case, because we're using light over the course of the season, we were able to track these trends with these experts and learn a lot from them. Also, I think one good thing about having plots like this, you can see we had them over multiple years. They basically show the same thing. It's more mites in the sections that we're not in. But because we kept showing the result over and over again, our logo and our name became commonplace for the farmer. So then when we went to talk to farmers, they already knew who we were. And that helps a lot with the credibility that you can get on these farms. Also, when you talk to the farmers, I'd say you should always ask, what would it take to pay? Or like, would you pay if? And then try to relate these data sets to it. Because then when you go back and tell the farmer how well it went, you could say, hey, it went as well as you said you would need to see for you to pay. And a lot of times the farmers will even give you LOIs. I mean, they're non-binding. So if you can get an LOI from a farmer, it really helps you later when you start to raise money. And talking about money, remember, I know this is a tech talk, but I just added this slide because remember, you are building a business here. It's really important that you don't get too far astray on the technology side. It's really easy to go down rabbit holes as roboticists and technologists in the market. And I think you really need to keep your head on straight when you start looking at where you can go with the business. And that starts from the very beginning. We focus a lot on picking the right market. So where are chemicals used the most? Where are they spending the most on chemicals? We found strawberries because, to be honest, it's 100 times more valuable than corn. Like, could we work in corn? Yeah, UV light works on mites, mildew, mold. This is pretty much in every crop. But in strawberries, we can make 100 times more money than we can per acre in corn. So it's the right place to get a business going. And yeah, once you have a really stable business, you can definitely scale into these other markets in the future. But if you don't focus on that first one, you're going to dilute your team across so many different places. It's going to be really hard to do a good job in any one of them. And I think also another thing that we learned was if you can replace a line item in the farmer's budget, in our case, we're replacing the pest and disease control cost. That makes it a lot easier to relate your value to things they pay for. And generally, I think that farmers are already spending money on the biggest problems that they have. So if you can't find a way to relate what you're doing to the farmer's budget, it's going to be a lot harder to start to sell to them. And the last thing on the business side that I want to say, it maybe is controversial because I think a lot of farmers want to see free pilots, but it's really important that customers pay. Like, paying customers is by far the most important thing because they care way more about your pilots if they pay. And if you can get them even to pay a little to start, then they're going to help you get that technology to market because you know they truly care about it, and their wallet is kind of already open. So later, when you start to commercialize, it's kind of like a normal thing to keep paying you at larger scales. And this is what larger scales look like for us. We got farmers to say, if it works, we'll do the whole farm. And that was kind of like our unlock for taking this from MVP to what I call MPP, which is minimum profitable product. I think it's all about the economics. You want to make sure that when you go from that small robot to the next step, which is a larger version of that, you want to make sure that you can do that profitably. And I got a slide just for that topic, because that's what we just got done doing. We basically went from the cheap MVP to, and I learned this from our manufacturer actually, it's the next step should be overbuilt. Like, you don't want to underbuild the next step, because what you're going to be doing is you're going to be taking that to commercial scales. And a lot of those things that you were doing that were unscalable before, like taking all those GPS points, well, it'd take me like a month to do that over a 100-acre field. So you really need to start thinking about where you can spend a little bit more money to reduce some of the scalability factor. And I think there's a lot of opportunities there. Like, you can, for example, the robot was getting stuck, get a motor with twice the torque you think you need, and it's going to save you that headache. And because your goal at this step is really to show the value at commercial scales. And I think at this step, another thing that we learned, we were literally taking like 20 gas cans in the back of a pickup truck, and we were like filling up our robots by hand. These new robots, they take more than 20 cans for one robot. So it would have been basically impossible to scale the fleet. So you really start to need to leverage partnerships. I mean, there's like a fueling company that comes out now and they fill up a big tank on site. We've got, like, we would need to buy a semi truck to move these things around. There's really amazing people that already know how to manufacture huge equipment like this, move equipment, fuel equipment. So make sure you're not doing things that aren't adding value to the customer. Make sure that you find great partners that can help you in that next step to scale. Also, I think continuously checking assumptions is really important. We were, like, one example is we were like putting up the GPS pole in the field, and we just did that from the beginning because it meant we controlled the whole process. We can make our maps and everything. And as we started to scale, we were getting on so many fields, we were putting up all these stupid poles. And we had a problem with one of our GPS units, and we're like, okay, our assumption that we need to put a pole up is not correct. We can get rid of all that labor and time that we were spending to put up that pole if we just change a little bit of how we run our systems. So I think there's a lot of cases like that as you get to this step, where just keep an eye out for blind spots. Like, things don't have to be the way that they were in the MVP stage. Also, I mean, this goes across like pretty much every stage of this development, from prototype to profitability, but just avoid shiny objects. I mean, we are constantly distracted, but always find our way back to the core. Like, what's the core value you're providing to the farmer? We've definitely spent time and money putting things like cameras on robots, and only to find out that the customer doesn't want to pay for it. So I think it's really easy once you get to this point where the farmers are starting to trust you. They're starting to tell you all these amazing things you can do to help them. And then you get distracted and you start working on those instead of just really doing that core thing really well. And this, okay, take any advice I'm giving you here with a grain of salt, because we're at this stage. So we haven't achieved all this yet, and these are things that we're doing now. One of the first insights that I think is valuable, and maybe some of the other companies that are further along might have an opposing view, but I think it's really important to scale with your first customers to whole farms. Because what I've seen is customers be really willing to give you their R&D budget, but to get past that friction point into their actual budget is probably the most important thing you can do. And if you work with 10 different farmers, then you're going to have way more lift on your team. So your team's going to have to do way more work with that than if you had just a few bigger customers that can give you the same amount of revenue. And those customers actually are a huge validation point. If other farmers know that these customers are taking a big piece of their budget and they're paying you, then other farmers start to trust you enough that you can really start to bring your technology to market faster. So we'll see if it's true, but in my opinion, scaling with your first customers all the way up to full farms is really key. We're also really focused on the cost of goods. So there's assumptions in your business model when you're starting out, and you're saying to investors, you're saying this business is going to really crush. It's going to be amazing. And in the beginning, you're validating the technology, but there's probably a few things that you need to do to make it a super high margin, profitable company. At this stage, we're starting to look at those things, like how do we scale our team with the robots? Well, we don't want one person with every robot anymore. It'd be nice if one person could watch 2 or 3 robots. That helps us at this stage start to scale the business. That becomes a friction point. Maybe hiring becomes a friction point. You start to scale the business based on the bottlenecks that you basically run into at this stage. And another thing is, like, when you have hard tech, this isn't going to be for everybody because some of you probably have software solutions, but if you have hard tech, it's really important that you took your MPP, which was overbuilt, and you don't forget to delete the parts that didn't matter, because you're going to learn a lot about the things that were way too overbuilt. You don't want to pay that for the next 30 robots. You want to really you want to pay that for the first couple, and then you want to trim and work with your partners to figure out where those opportunities are. This is counterintuitive, but you're also going to start adding more to the system. And I think the one really cool example that we found, it wouldn't have been cool if we didn't have a person there, but we had a person on site, and there was a coupler this big on the top of a 6-foot-tall tire that came a little loose. And that robot, which could have been autonomous and nobody watching it, its tire was 15 degrees off, and it became a plow in the field. And it was starting to plow the strawberries, but we had a person there. So we were able to catch that, learn that that coupler is a failure point that we need some redundancy around. So adding technology at this stage, when you're starting to think about scale, it's kind of okay to add some things at this step. And then the last point I have here that we're leveraging, but you have to be really careful with, is equipment financing. If you're going to be a service business like us, then CapEx is going to be one of your biggest constraints. And if you built your business based on profitable economics, you're going to be in a position where you can start working with the banks. And that is really valuable, because otherwise you end up needing so much equity to build this fleet of robots that your valuation kind of balloons. So if you can build the business around profitable economics, I really highly recommend that, because you're going to be able to leverage some of these other financing tools that are going to help you grow. And I just added this slide because growth in the future is a lot of like what gets people excited here. Once you have that profitable foundation, you've got market leadership, you've got trust with the farmers. This is like, it's like slow to go fast, because once you have that, now the farmers, they probably grow more than just strawberries. You know, they grow 3 other crops and they trust you. So now you can take that technology and other technologies and scale really rapidly on top of this fleet of robots that you've built. And the profitable foundation gives you the cash flow to do that without a ton more investor dollars. So I think it's kind of like a slow to go fast future. And we're at that inflection point right now where we're starting to get that adoption at full farm scales. And we've already started to see this. We just added last year the vacuums, believe it or not. So we were doing UV light, and the farmer's like, can't you add vacuums to it? And we got 100% adoption across all the robots that have vacuums now. The farmers were like, yeah, give me some vacuums. And double the price, it's the biggest dial to margin. So if you want to increase your margin, if you've got an autonomous platform out there and you can add something to it, I think these are 2 AI-related opportunities that we've explored. Thank you, Lee. And I think these are some of the opportunities that we can, in the future, start to upsell to these customers. And that's been our journey. I hope it was kind of helpful, and there's like some lessons learned for some of you in the audience. Thanks.
All right. Thanks, Adam. We got probably a couple minutes for questions, if anyone has a question from the audience. There's some mics floating around. Here we go.
Yeah, sure. So there's this thing called bug vacuums. It's like a tunnel that they run on the front of their tractors today. And it sucks up the bugs that we don't treat with light. And there's the baffles. It's almost like a bug on a windshield. The bug accelerates up into these baffles, and it kills the bug that way. Again, another non-chemical solution. They run at about the same amount that we run lights. So they're like, can't you just run that too? Yeah, we reduce it's something that I like to think of as an IPM strategy, and that's integrated pest management. So it works well with other things, and depending on the comfort level of the farmer, some farmers don't spray anything for mildew, for example. Other ones, if they've got a lot of fog settling in on the field, they'll spray something too, but much less. We can replace up to 75% of the things that they use for mites, mildew, and mold in strawberries. Yeah. Yeah, it's an 8-hour shift, so we run 6.5 hours of operational time with the robots, counting breaks and setup. And it's an autonomous path, so it's a pretty simple path. It's GPS points, and a good GPS signal allows you to navigate the field based on those points. But we do not do everything. I would say that there are definitely cases in the field, and it's good that we have a person there still now, because there's, like for example, point rows. It's like square field, really easy. You can turn at the end and come back. But point rows, man, sometimes you're shimmying quite a lot to get down the next row. So this is some of the technical debt. As you start to scale, these are the types of solutions that you solve next.
Perfect. Okay. Thanks so much, Adam.
Thank you.
Thank you very much. Okay, next I'd like to welcome Nick Fisher. So Nick Fisher is the CTO of Autonomy. Nick is a multidisciplinary technical and product leader with expertise in robotic autonomy, systems architecture, and software development across ground, airborne, and maritime platforms. As CTO of Autonomy, he drives technology strategy and product innovation, applying his background in advanced autonomy and systems engineering to deliver solutions at commercial scale. He's passionate about building highly capable engineering teams and leveraging cross-industry technologies to accelerate automation in the field. Take it away, Nick.
Thank you. All right, hello everyone. My name is Nick. I'm the Chief Technology Officer for Autonomy. Today I want to dig a little bit into what it means to focus on rugged autonomy. Kind of terming something new here, but these operational environments that a lot of these machines that you'll see this week are working in, they're not very well structured. They're not simple cases. They are not lab environments, and so there's a lot of real-world scenarios and problems that you have to kind of think about and solve for in order to really add value to a grower that wants to use these types of technologies in their applications. So let's first talk about some of the challenges that we typically see. I guess I should start with what Autonomy is focused on. We are trying to help automate a lot of different types of work tasks in high-value specialty permanent type crops right now. And we do that through partnerships with OEMs such as Bobcat and Kubota to build a factory-fit autonomy solution that allows you to automate a whole variety of different types of workloads, mostly focused on pre- and post-harvest tasks for these types of crops. And so some of the challenges we typically run into are really around how these environments are set up. You might have uneven terrain. You might have certain scenarios where the ground cover exists. You might have certain scenarios where the actual task you're doing, maybe you're trying to mow a cover crop, but it's the beginning of the season and the cover crop's 3 feet tall. How do you actually effectively build an autonomous solution that understands the difference between what's safe to actually touch and what's actually the responsibility of the task you're trying to solve for? You certainly have dust, you have fog, you have all kinds of different types of point rows and scenarios. You might have water or low spots that the vehicle might get stuck in, or muddy conditions. And if you can't solve for all these different types of scenarios from an autonomous perspective, then the value proposition of these vehicles doing automated work is really limited, because someone's always going to have to go help these systems out. So how do we think about building an autonomy solution that allows you to handle all these different kinds of edge cases and scenarios? And that's really what Autonomy has been focused on the last few years. So in order to approach some of these, let's skip 2 slides. There we go. In order to approach some of these problems, we really we've adopted physical AI. So what is physical AI? Physical AI is the embodiment of machine learning and perception and cognition into a physical machine. I think if you think about robotics these days, the hot button topic is, humanoids can do everything. Humanoids are built for a world built around humans. But if you think about farming and you think about industrial markets, these parts of the world are actually built for machines. They are optimized and designed to be automated by industrial systems. And so how do we put a lot of those same pieces of intelligence into these types of machines that are really good at doing the type of work that is required to actually grow food, grow different types of crops needed in the food supply chain? And so we have, like I said, partnerships with 2 different OEM partners. You see a Kubota tractor here on the left, and you see a Bobcat tractor here on the right. And we work with them to help automate a whole variety of different types of things. We'll talk a little bit about some of the technologies then into what goes into the physical AI that we've built. So there's a couple different kind of screen renderings here. It is a full self-driving system that runs on these tractors. So it is similar to what you would find in an automotive vehicle. They have a perception system, they have a planning system, they have a control system, and it allows them to perceive the environment and make decisions based on what they see around them. And it also allows them to generalize to different use cases. So we can never solve for all of the different scenarios that these tractors will come across. But what we have to do is build systems that can generalize around the edge cases that it doesn't know or hasn't actually been trained on. So today, our systems run in a variety of different crops. They run in table and wine grapes. They run in different types of orchards, apples, olives, citrus, stone fruits, nuts. And we've built one system that generalizes across all these different types of use cases. They're focused on trying to solve the problem of how does it safely navigate the structure of the environment when the structure exists, but then handle scenarios that when structure doesn't exist, you have occlusions, you have canopy cover, you have organic matter that might be in the way. How does it keep going? How does it make sure that the work that's being done can still be efficient, even if it's handling challenging scenarios? To talk about some of the work we do, so I mentioned we're in different types of crops. The other really cool thing about the Autonomy platform is it's generalized around a whole different type of classes of work. So you see here a variety of different implements. The tractors that we're building Autonomy into, they're Swiss Army knives, right? They can do a lot of different types of things. So I think we have something like over 100 different types of implements we support today. The value for a grower is not that useful if the machines can only do one task. The real value is when they can do lots of different tasks that effectively help solve all the different types of scenarios or work that needs to be done on the farm. So we have a couple of classes of work that we support today on our platform that's continuing to expand each year. Today, those classes are around mowing, different types of spraying, could be air blast spraying, electrostatic spraying, herbicide spraying, different types of mechanical or non-chemical based weeding techniques. The green image here is actually a weed knife based system that does mechanical weeding in vineyards. We also do seeding, disking, tilling, any variety of pre and post harvest tasks are kind of what we're focused on now. A lot of different things where you would traditionally require someone to be sitting in a tractor for hours and hours and hours driving that system. That is what we are focused on automating. The other piece of cool technology that kind of exists related to the implements is our system generalizes against the feedback related to how the work actually gets done. If we just drive these systems around, it's not that useful. If we drive these systems around and do the work poorly, it's not that useful. The work has to be done correctly, and we have to prove that we can do the work correctly. And so there's feedback loops between the implements and the vehicles that allow the autonomy to be reactive to how the environment and how the work is being done. This could be done with a dumb implement, something that's just PTO driven, or it could be an intelligent implement that actually has communication protocols and we can actually communicate with directly. Our system kind of handles all those different types of implements and uses as much information as we have available to make sure we do the work correctly. The next thing to talk about is how beneficial something is if you can only do a small amount of work on a small property. So I think Adam mentioned one of his recommendations is scaling from an R&D project to a full site operation, and that's really critical. So we're doing this today, and we have a process that allows us to actually fully set up an entire farm from the beginning, day one, the first time you receive our platforms. We do this because we digitalize the properties entirely. This includes understanding where all the blocks are. This includes understanding where all the road networks are that allow you to connect through the blocks, all the private road networks. Can't run Autonomy in California on public roads, but at least most of the sites that we operate on today have private road networks that connect most of the facilities. And then it also comes into play that we don't have to do this mapping procedure with the vehicles themselves. So no GPS waypoints, no driving the tractors around to build maps. We do this all ahead of time, and so when the tractors arrive, they can run whatever block you want that first day. This is a really critical scaling thing that has allowed a lot of the customers to be super thrilled that they can do operations with these autonomous systems across all the different types of work they need to do without it having to be a slow roll of saying, oh, you can only run these blocks or these certain areas. This is complicated. Like I mentioned earlier, there's point rows, there's creek beds, there's all kinds of different shapes and sizes of these properties, but the autonomy system is able to generalize across them. They're able to build complex routes in real time. and solve the navigational aspects, obviously, that get coupled within the work automation aspects. I think the last point I want to talk about here, you see the video on the right, is the multi-vehicle aspect of our platform. So if you just replace one tractor driver with one autonomous tractor, it's not that useful from an ROI perspective. Where you really get interesting, we talk a lot, you'll hear a lot at the show about labor shortages and the ability to find people who can do this type of work. But when you have now one operator who can use their cell phone to operate 5 to 10 tractors themselves, it's a huge multiplier in efficiency in what they can get done on the farm. And so our core platform and our user experience is built around multi-vehicle operation because it's really critical in order to add value. So talking through that user experience, we today have a tablet-based experience and a mobile phone-based experience. It's really tricky to come into the agricultural market and not overwhelm a grower with technology. It's really critical to meet the grower where they're used to operating, to make sure that we're, as a technology company, not coming in and saying, hey, you should farm this way. We don't want to teach you how to farm. What we want to do is give you tools so that you can farm more efficiently and you can farm with superpowers. So that is what the user experience of our application suite is kind of built around. The general workflow for a high-value crop would be you choose the block you want to do the work in, maybe one or more blocks that are pre-mapped as digitalized versions of your property. They're all named the same. The row numbering is the same. It matches how you expect your property to be set up. You configure what type of work you want to do. Let's just say you want to do air blast spraying. You say, I want this rate of variable rate spraying from my air blast sprayer, and I have 3 tractors that I have to complete this work. And then you send that configuration to your individual 3 tractors. They, on the tractors, they route themselves across your property over to the block where the work gets done, and then you can monitor that work as it's happening and get feedback and information along the progress of the way. When the work's done, when they're done with their passes, they return back to your shop, and you can configure them, reload, and schedule something else to go out next. And so that's truly how our application suite works and how you really go from I'm an operator who I know what work I need to do to, okay, I can use my phone to just configure the tractors to do that work for me. We talk about the long tail of edge cases with autonomy. There are going to be problems. There are going to be tricky scenarios that the tractors still get stuck in. Obviously, this is really important to the efficiency of the work being done, and we want to minimize this. We have core KPIs. I'm sure everyone at the show will explain to you about wanting to get tractors unstuck and keep going. That is part of the technology roadmap. We don't, at Autonomy, believe in teleoperation. So there's never really going to be a use case where we find it appropriate to say, oh, this tractor is stuck in the field. Let me have some remote call center dial in and see if we can get it unstuck. Maybe it's stuck in mud. Maybe it's stuck because there's a piece of equipment that got left in the field and it can't move it. A call center is not going to be able to recover that. So what we've done is we've built into our application suite a way for growers and operators to have control over helping respond to when tractors actually need to get assistance. This could be due to puddles. This could be due to equipment that's left. It could be a turkey that's just rummaging through the vineyard and you want to honk the horn on the tractor to see if the turkey will move out of the way. What we want to do is alert the system through notifications so that a grower can pop open their phone and be like, yeah, no big deal. That's just a false positive. Like, let's just continue that on, and then the tractor resumes. Or they pop open their phone and say, someone left their truck at the end of that row, and the tractor needs to get through, so let me ping someone and see if they can go move that truck. But that level of responsiveness that's built into the application suite is really what allows these operators to try to get as much continuous operation as they can, even when things happen. The team really wanted to put a different word here, but we went with stuff. Okay, and so I think this is towards the end of the conversation, but the last point I wanted to make here is that Autonomy is at a phase where we are not just building prototypes anymore. So we are fully deployed in various parts of North America and in Australia as well, and we have productionized systems that have been running for several years now with real customers at full site scale operational full site operations. The growers have rich metrics and KPIs that they're able to view about the performance of the systems, what work is being done, where they have efficiency, how the operators are using our systems, and where maybe they need better training. But we've really proven this out over the last few years through various stages of trials with certain customers, and now we have a lot of growth and adoption across a lot of major enterprise growers in North America and Australia to take this system to the next level. We're continuing to expand the different types of use cases and implements and type of chassis and tractors that we're working on. Today at the show, you will see a 50 horsepower Bobcat tractor and a 100 horsepower Kubota tractor. That portfolio of Autonomy enabled equipment, both from a smart intelligent implement and a smart intelligent vehicle, continues to expand. But we have demos today that you guys are welcome to come out and see soon. And that is it. The future of these machines helping to automate a lot of these tasks is really exciting. I think the host mentioned he saw a lot of equipment running. We would love to have that equipment be automated so that the individuals that are on the properties can focus on the really critical things that are actually difficult for tractors to do, and allow the really mundane, tedious stuff that the tractors, the boring stuff, to allow the automation to handle those types of things. So that is the presentation. I'm happy to take any questions.
Nick. We have volunteers actually with microphones. So if you have a question, just, oh, there's one in the back there.
For the mapping aspect that you mentioned, you said you're not using vehicles to go survey the field and stuff like that. What are you using?
So we can import information about the property that you might have, or we can use aerial imagery to help digitalize the property. It kind of depends. Some growers have that information ahead of time because they need it for the other reasons. If you don't, then we can digitalize it for you.
Got a question up in the front here. Oh, yeah, go ahead.
How do you communicate between your mobile device, the iPad or the phone, to your
Yeah, great question. So when we first started, everything was cellular based on the tractors. We've basically built a solution that doesn't always need GPS. So GPS can come and go. That's fine for our system. Obviously, GPS under canopy cover. Sometimes when you're near buildings, there's multipath problems. But the system uses vision for most of the navigation, but also be internet tolerant to dropouts as well. So when we first started out, there were some scenarios where there'd be big blocks of space that just would have no cell coverage. And that was a big problem. So we had to design a system that could tolerate that. The Autonomy, when it's running, doesn't need internet. Now, all of our fleet of tractors have Starlinks on them. The technology has evolved. This is a great use case for agriculture. These vehicles move really slow. The Starlinks stay connected the entire time, even though they're doing their operations. So the systems are still almost always internet connected. Obviously, if you want your status feedback or your metrics to be real time so you can help manage an intervention or see the progress, then it needs to eventually have some intermittent connectivity to show progress. And so we find through the combination of cellular tech and Starlink that the vehicles are almost always connected, and that kind of meets the need of what we're doing.
follow-up question. What level of accuracy do you need for GPS operations?
So the vehicles have RTK GPS. They have 2 antennas on them that allows us to get differential heading estimates out of the RTK. But it doesn't need it all the time because we have a vision-based navigation system. I kind of glossed over that pretty quickly, but we have a full vision-based navigation system. It only kind of sometimes needs GPS. We use it when it's available. It's a great sensor for ag because it's almost always available, but we are tolerant to when it's not available. If you have a lot of tree canopy, there's a lot of vigor, or you have big trees on the side of properties, the GPS does degrade. It goes down to single fix sometimes. It will recover back into RTK. We use the best measurement we have available, but it can go for long periods of time and still navigate even with complete GPS loss, and it doesn't care.
What's the fastest speed you allow the system to run in autonomous mode?
So we run somewhere, the maximum speed we do right now is like 5 to 6 miles per hour. Most of the workload actually dictates the actual speed of the operations. Like if you're on a road network, you're like traversing the property, we let it go faster, it's on the road. But most of the actual tasks like mowing and spraying and stuff dictate a little bit slower operation. It's pretty flexible though. We can generally work at whatever speed the vehicles are capable of running at.
From a perception point of view, do you have a LiDAR?
The sensor stack, yeah, as you can see in this photo, so there's 8 cameras on the tractor and then a single spinning LiDAR. Most of the navigation is all vision-based. The LiDAR is a redundant sensor, but we think it's good for some use cases. It's not great for all use cases. It doesn't handle fog well, for example, so you get early mornings. Like if you built a solution around a LiDAR tech stack solely, you wouldn't be able to work any morning that there's fog. So it's a sensor fusion type solution around these things. It uses the best sensors that are available at any time.
Do you have any machine-to-machine communication?
There is some. So the scenario that I like to give as an example for the machine-to-machine communication that's important is imagine you're running one block with a couple of robots, with a couple of tractors, say 5. Every time they're doing headland turns, they have their own like little chunk of segment, but there's some deconfliction scenarios where they actually, they might detect each other and say, oh, there's a tractor, I should like do something different or try to go around it. But like if they're both stopping because of that, someone has to deconflict the other one. So we have some logic. Like I said, because the tractors are almost always internet connected, they communicate through a centralized communication protocol. I think early on we had ambitions that we would probably need to do a V2V that was like a radio-based system. But now that honestly, now that the Starlink kind of keeps these systems mostly always connected, they don't need the V2V, yeah, or they don't need a point-to-point based radio network. They can do it through the internet.
Have you got any data on effectively the uptime of your autonomous solution? So, you know, assuming a good operator is driving a tractor and doing the operation, they're driving 100% of the time.
Mm-hmm.
You know, obviously, the machine's going to get stoppages now and then. What percentage of that 100% of the time is the tractor operating the field operation?
Autonomously?
Yeah.
It's generally more time because, I mean, without going to numbers, it depends on what the operators are intending to do. If it's a task that is highly automated, let's just say it's mowing and they're going to mow for a week straight, generally speaking, the autonomy systems can run longer than a human operator can because of shift lengths and those types of things. Where we see the real ROI is where that same operator can be running 3 tractors in parallel. So they effectively can do way more work than if they were doing it themselves in the same number of hours. So we don't have a lot of customers that are running one tractor. Every one of our customers runs multiple tractors because that's where the value is.
Okay, thanks so much. Great talk, Nick. Okay, it's my pleasure to welcome Nathan Bivens to the stage. So Nathan is the CTO at Fort Robotics, where he leads the development of trusted control systems for autonomous and semi-autonomous machines across multiple industries. With more than a decade of experience at the intersection of robotics, wireless comms, and functional safety, Nathan brings a safety-first mindset to solving the complex challenges of machine control in real-world environments. He also leads Fort's work on proactive safety for AI-driven systems, including a collaboration with NVIDIA to advance safety across the autonomy stack. Take it away, Nathan.
All right. Well, thanks, Chris. I hope you can all stay awake because, you know, the guy's talking about great autonomy systems, and I'm going to come in here and talk about the amazing topic of functional safety. It somehow keeps me interested for the last 10 plus years in this world. So actually, interestingly, we work with a lot of these companies, both Trick and Autonomy are customers of ours. So Fort has been around since 2018, but actually comes from a previous company called Humanistic Robotics, which developed the system you see there for the Department of Defense. We got a contract back in 2012 to build an autonomous system for landmine clearance, which, as you can imagine, is probably one of the most obvious solutions that ticks the 3Ds of robotics: dull, dirty, and dangerous. And very clearly something that if you actually find one, you do not want to be around when it goes off. So developed the solution, the landmine roller out front there that you see in front of that Terex, but then said, hey, we got to automate this thing. And very quickly realized when using the kinds of sensors and the kinds of autonomy that existed 13 years ago, this was a very dangerous thing to automate. That machine could go 15 miles an hour. Like I say, it could drive faster than I could run. So it was very important that we could maintain safety while this thing was operating. And for us at the time, it was about developing a wireless safety solution, which we could not find in the market, that met all of the functional safety standards that have been well established in the industrial world. But something that we could use wirelessly in the field in pretty unstructured environments. At this point, we have over 16,000 devices in the field. Actually, by the end of the year, it'll be pushing 18,000. 650 customers. The reason why we have so many customers is we run across industries. So construction, mining, obviously agriculture, turf care, and a lot of the humanoids actually we work with as well in developing safety solutions beyond the world of communications. We spent a lot of time doing this. Like I mentioned, our goal was to do this to the existing industrial safety standards. So we have multiple third-party certifications to IEC 61508 SIL 3. If you're familiar with the world of functional safety, it's about as rigorous as you get without getting into the kind of process control standards where you're worried about things like nuclear reactors and oil refineries. That's me. He already told you about me. We don't need to talk about me. I have a long background in electronics and various things from the commercial world all the way through to obviously safety. So I'm kind of going to drop a bomb out here. Robot safety is broken. We work with so many customers. I've seen so many people trying to solve this problem. They spend so much time and so much money trying to figure out how to deploy their robots, right? That's the whole point. We wouldn't be here if we weren't building machines to do things better, more safely than how you could do them with a human operator. One of the key things you have to do, especially in unstructured environments like agriculture, is you have to worry about safety. Problem is that the people who build the robots, like, you're not safety engineers. You don't spend your time worrying about things like failure rates and diagnostic coverage like I do, and you shouldn't have to. But you're provided with tools that were largely built for the third and fourth industrial revolution, which are generally bolted to the floor in warehouses, in manufacturing environments and warehouses to an extent. They're very inflexible. You program them once, they're designed to be programmed once, turn the production line on, you probably never touch the safety system again until you maybe need to revamp that thing 10 years later. Then we throw AI in there, and machine learning. These systems and the standards have no idea how to deal with AI. So any kind of machine learning system really cannot meet the standards as they exist today for functional safety. They're very long to design, and I know this both from our own experience of going through functional safety certifications. The process of going through and designing a system, testing it, certifying it, just adds so much time to the design cycle, both for our own products as well as our customers who go through this. Everything's connected. Nick was talking about how they have these highly connected systems. They don't need to be connected, but they are. Increasingly, we hear a lot of people worried about cybersecurity for very good reasons, including developments in the European Union with the Cybersecurity Resiliency Act, the Machinery Directive becoming the Machinery Regulation. So accessing Europe now is going to require cybersecurity as part of any safety or product certification. And really what this leads to is that you have a whole bevy of solutions you could bolt on. I say that you could bolt them on after the fact because you as a robot developer are worried about solving a problem, not necessarily safety. So you add safety on once you've gotten out of the lab and you want to deploy it in the field. The problem is that you end up with much larger, much more expensive solutions because they're not really designed to solve the problem you have. They're designed to solve the problem that existed 10 years ago when the first LiDARs, or even far longer than that, when Dr. Sick was patenting the first LiDARs 30 years ago, 40 years ago. So what we've seen is the large-scale deployment of robotics actually has been really hampered by this lack of safety solutions that are really designed to meet robots, especially in unstructured environments, where they need to be. And you throw AI in there, and there really is just nothing fit for that purpose. So I want to start in talking about how we're going to solve this and like how we at Fort think about the future of agriculture. Like I said, we see a lot of different industries, but I think it's important to talk about like what in the world would safety even look like in the world, this future of agriculture. And I think Nick was talking about how they deploy these systems. It's almost never one-to-one with a human, right? What's the point if you're just taking the person off of the tractor and saying, well, now you get to stand there and watch the tractor drive. It doesn't really solve much of a problem. It's good for a proof of concept, but to deploy, to be really useful, it has to be many machines operating in a flexible environment across a wide geographic area. Machines have to be reusable. Unless you find a really, really valuable application where you can develop a single-purpose machine that just runs constantly, you really need a multi-tool, right? I mean, the tractor is kind of the multi-tool of the farm. I grew up throwing hay and harvesting corn in Pennsylvania, so we use these tractors for everything. It's the multi-tool on the farm, and why would we expect a robotic or an autonomous system to change that? Obviously, the systems need to be connected because if you're going to have all these things roaming around, you need to know what they're doing. They need to be able to tell you if there's a problem. So that connectivity becomes critical, but it's difficult to do. You can't rely on it all the time because it does come and go. Human intervention. So, all these autonomous systems are really, really great. They're very valuable. They're really important that they can run autonomously most of the time. But to gain trust in the systems, you still need a person around who can intervene if they know something's wrong. Like the scariest thing for people is when you see a machine and you can't stop it if you know something was happening. And you can't place restrictions on the environment. I'm not sure, somebody said it earlier that these especially in agriculture, they're designed for machines, but you can't tell a farmer, okay, my machine is super powerful. I can solve all your problems in your farm. You just have to completely change the way you operate. It'll never work. You're not going to take thousands of acres and change the way their fields are structured. It would be so expensive. It's just a bridge too far for most people. So it's really, really important that you meet them where they are. And these places are too large to put up fences to from a safety standpoint, guarantee that obstructions won't occur, that any of these things that you don't want to happen, like you don't want to run over a person, obviously, but animals, any other obstructions, a tree falls down, you have to deal with all of these scenarios, and from a safety standpoint, ensure that the machine will behave in a predictable and ultimately safe way when they run into these scenarios, because we just can't exclude them. And you have to minimize site setup, right? Like I mentioned, you can't tell the farmer that they need to change the way all their fields are structured. It's just not going to work. So how do we get there? Where's my text? There we go. So to accelerate robotics from a safety standpoint, you need infrastructure. And I think that Adam said it earlier, that as a robotic developer, you have to focus on the things that are actually valuable to your customer. So you talked about developing their solution around like how do you use this UV light technology and deploy it properly on the field to actually see the results to reduce the need for pesticides. Great, that's exactly what you need to do. But too often we see customers get caught up in all of well, how do I build the robot? How do I deal with all this other stuff that's out there? How do I have to go build these complex systems that go through all these proofs to ensure that I have safety all figured out, which is important. But you need to figure out how to spend less time on that and more time on the thing that actually makes your solution actually work. Nick talked about this, human-centric interfaces, right? No matter how autonomous we make these systems, they still have to have people in the loop somehow. They might be moving from what we used to call human in the loop, where there's actually a person watching, to human on the loop. Typically, that's when it's a one to kind of many situation. It's still very important, though, to provide the interfaces so that the people can know how the machines are behaving without requiring months of training to do so, because we're not going to be in a world where you're going to have highly trained, multiple degreed engineers that are monitoring these systems. To think about that person that used to be driving the tractor now is probably going to be the one who's monitoring and managing these systems in the field. So meet them where they are. And scalability. I know a lot of companies, when they first start, they might have a one-to-one deployment. They're going to have one machine and one person watching it. Clearly not the best solution, and really not scalable. So how do you build a scalable solution that grows from that one-to-one, which is where we usually first start working with customers in a one-to-one system. They're trying to get it out the door. They need something that they have a safety argument around that they can deploy, and typically makes the lawyers happy that they have a system that actually can meet these safety needs. But they can grow and maintain that same safety case across a larger deployment of one to many, one human with 3, 5, 10 robots. But then it also needs to scale from a rules standpoint. So if you think about the way that the safety rule sets are structured, right? You're going to have standards that are set, IEC, ISO standards, or Cal OSHA that say these are the rules you have to operate. But then there's also the machine OEM is going to say, hey, I'm going to put this system together, and I know this particular tractor has certain limits, and maybe in a row has this speed limit, and on a road has a different speed limit. So you could have GPS, geofencing or something like that, saying different zones of operation, I have different rules. But then they might go to a site, and the farmer might say, well, I have to have different rules because I have a different speed limit for whatever reason on that road, or it's a rainy day, so I don't want you tearing up my grass, so you need to stay off that on rainy days. So that you have to have a scalable set of rules that allow these kinds of flexible deployments. And then the last thing, which I'll get into, what we call context-aware safety. So this is where we're worried more about having the safety systems be smart enough to actually do all these things. Because today, like I've said, a lot of these safety systems are extremely inflexible and fixed. So I don't know why I did that. Context-aware safety is what we believe and what we've been working on that enables systems to be much smarter but still meet these safety requirements. So what is context-aware safety? The traditional safety world, you can see it kind of labeled the bottom where, that existing functional safeties, this is all the standards-based stuff, the things that we have done for 10 plus years, called reactive safety. So this is where generally a human or a simple sensor recognizes that some safety hazard exists. This is the world of 2D safety lidars that are just scanning a field 6 inches or a foot off the ground. If something comes within that zone, they trigger a signal that says stop because I can't hit that thing. Obviously, I don't know what that thing is. It's something. It could be a box, could be a person, could be a bad reflection. I don't know, but something was within that came within a certain distance of my robot because I programmed the safety scanner. It is going to tell me every single time to really high level of reliability that something triggered that scanner. They're great in more structured environments, although I have to say that even in the structured environments like warehousing, customers have their problems with these because they tend to have a lot more stops than they need to. Because if you think about in a warehouse, it might be a person that you stopped for, but if it's a cardboard box, or what's worse, a puddle that looked like a box because I got a bad reflection or looked like something was there, now my AMR that's running packages around the warehouse is shut down and stopped in the middle of the floor because it thinks something is there. But it has no way to determine what the heck that thing was because of this very basic reactive safety system just isn't smart enough to do that. And that's the world we had to be in for a long time. Context-aware safety moves everything to the left. And this is, I borrowed this from a guy named Riccardo Mariani at NVIDIA, who's working on a lot of this proactive and predictive safety. As you can imagine, they're very tied into this with trying to drive AI into this. We'll talk about where the intersection with AI is. But that context-aware safety is about identifying the things before they happen So before I have to stop, I can see that maybe there's a person there because I have some context, and I might know where I am, and I might apply a different rule because of what's there, where I am, the speed I'm operating, the mode of operation I'm in, and applying a different set of rules while still meeting all these functional safety standards in order to meet these requirements. Next one here. So I've been talking about the safety we have today. Really simple. This is sort of a very basic flow chart of what like a 2D LiDAR or any of these basic distance, like, hey, is something too close? I'm going to stop. It's really inflexible. It doesn't know what's there. It just does exactly what you said every single time. So context-aware safety, like I was walking through before, it allows us to make much more sophisticated decisions that leverage modern perception. And this is that moving to the left out of the world of just reactive safety and into this proactive safety world. The place where it really gets complicated is this AI-based object classification. And this is a thing that I mentioned NVIDIA earlier. There's standards work going on in the ISO world. If you really want to dig into it, you read DTR 5469. It's what's going to be an ISO standard for the classification of AI systems for use in safety, and that allows us to do things like actual object classification using an AI-based system, a machine learning-based system, to identify things, whether it's using cameras or LiDARs, whatever sensing you need, to identify objects and classify what they are, not just that they are there. And that allows us to make much more sophisticated rules or sophisticated decisions based on rules so that we can make better calls, not just from a safety standpoint, but ultimately from an operational standpoint, reduce downtime, and just basically run better because we don't have to rely on, from a safety standpoint, these really simple rule sets that are just, again, something got too close. So I talked about how this behaves. This is a little bit of how it's structured. There's a concept we're kind of borrowing from the autonomous vehicle world called mixed criticality. In traditional, and I realize this is probably oversimplifying this for the roboticists in the room, but from a functional safety engineering standpoint, a lot of the things that you talk about as being safety responses within your control system are not actually safe from a safety engineering standpoint, because I can't quantify how safe they are. So all of that stuff from my functional safety centric view is in that red box at the top, and I call that autonomy, and I say I can't trust it. It's going to make a best decision. It's probably great. You've tested it. You've run it in the field. It probably 99.99% of the time will make the right decision. But I'm worried about another 6 or 7 nines of reliability for dangerous failure, meaning I'm not going to do the dangerous thing, hurt the person, whatever those hazards we've identified are. So what FORT does, and what we're developing in compliance with these safety standards, is the supervision layers that fit in between our existing reactive safeties to this world of e-stop buttons and things like that I identified something was there. The supervision layers on top that can leverage AI and hit less stringent safety standards than this sort of SIL 3 world of reactive safety, the e-stop buttons that you have, but still can layer on top and provide safety responses to avoid the need for those reactive safety responses of just stop because we're going to hit something. So again, that's where that proactive piece comes in. If we can identify the hazards by being smarter about understanding the world we're operating in, we can avoid the need for the worst case scenario, which is stop the machine because something bad's going to happen. Still have to have that. That's all part of the larger safety case. But the goal is so that lower blue layer ideally never, ever, ever, ever gets triggered. So you can kind of see, like, the ideal case is the red in the top is running in control and we never have to worry about the others. But the yellow and the blue layers come in because the world isn't perfect and there's always some new scenario we have to deal with. And at FORT, what we do are those unexpected things. little bit about how we actually do it. We wrap around these AI systems. There's some work we have to do in supervising the actual autonomy behavior itself, but a lot of it is really just enabling the infrastructure, both from a safety standpoint and also because we work with all these robotics companies, we see all the things they struggle with. So we're trying to pull together some of the other, data collection, security, and some of the communications as well, because they're problems everybody has to solve. So why not provide those? But for us, obviously, safety is the core thing we've worked on for a really long time. So still a little ways off here. You've seen it. We've had a couple of different announcements with NVIDIA on some of this. They're very focused on the humanoid world, but all that work that we're doing with humanoids and AI safety applies, across the spectrum. And if you're not applying AI today, you probably will in the future. A lot of the stuff would still would be useful, but as you look more towards AI-based systems to make your machines smarter, definitely like to talk about what we can help you with. I think that's it. Yep. Right on time.
Well, thanks, Nathan. That was, that was really incredible. I know that our automated tractor has a whole safety committee, and all they worry about is those, those multiple nines you talk about. So
We're always the ones that tell you, you can't do that. You just can't do that.
We have a team actually called Gretzky, because it's, he was number 99, and so we're at 99.9. So
Yep.
we have a team called Gretzky at work. So we got some time for questions. So if you have a question, just raise your hand, and then someone will try to run around to you with a mic. There's one over there.
Before I walk away with you.
Oh, sure.
Nathan, thank you for your presentation and the focus on safety. I was curious with the kind of lack of rules and regulations right now. Are the manufacturers stepping in with how to maintain these autonomous systems? And because clearly that's something that I'm concerned about.
So I'd say that I would have said a few years ago it really is the Wild West. It's getting a lot better. I have to say that I know Cal/OSHA has been pushing some things around how their autonomous systems are deployed specifically in California. Obviously, that's driving some of the manufacturers. The other thing that we see a lot of is just the European regulations. I know that may not be a huge concern, but from a business standpoint yet for a lot of the robotics companies, they're focused, obviously, California specifically, there's a lot of market here. And Australia has kind of similar guidance today. But Europe is driving a lot of the regulation around this. I think that the manufacturers certainly are doing some. I think that they're cautious. I know that John Deere's, I've seen some pretty amazing things that you guys have worked on that I've never seen the light of day that I'd love to see out there. And so I know there's a lot of great technology that may be being held back because of safety concerns. It's where the lawyers who got to figure out how to appease the lawyers. But so I think that there's a balance there. I think that the OEMs are doing a reasonable job, but we need technology and some amount of regulation just to say this is what's good enough, because I think without that regulation, it leaves everybody kind of up to their own devices, which usually, honestly, means they're extra conservative, especially the big companies, because they have big pocketbooks that people can come after. The lawyers get worried. So what we see is companies with great tech are afraid to deploy it because it just isn't the regulation to say this is what's good enough. So it's difficult to pin down what's safe enough. And anybody you've done hazard analysis, it can be a really daunting thing when you think through all the potential ways something could go wrong. So I'd say it's a mixed bag, but in general, we work with a lot of those OEMs. I think they really try to do their best, but I personally would like to see a little more. I hate to say regulation, but it's more like guidance. What is actually safe enough? What do you really need to worry about?
One more over there.
Thank you. You said a little bit about redundancy, and I thought that was very interesting, but I wanted to hear more. There were some areas where you say not everything might need a redundancy for safety, but I liked that what you said is best if it's perhaps never used, but it's good to have it there for safety. Can you tell me a little bit more about that point?
Sure. So redundancy was the only solution for safety a long time ago. Well, not a long time ago, 10, 20 years ago. It's like qualitative safety analysis. Well, if I have 2 of something, I'm less likely to fail dangerously. The world today is much more quantitative. So in that, we're more worried about how often is it going to fail. Because I'd rather have a system that's going to fail once every billion hours that's a single channel than a redundant one that's going to fail every 1,000 hours. And I see that all the time, where people have redundancy, but then when you actually look at the failure rates of the parts in that redundant system, it's really not an effective solution. So redundancy is a critical thing to consider, but it's not the solution. So you have to generally have to have a much more sophisticated analysis to determine what will cause the failure, what kind of failures are we actually worried about, and what approaches are more effective in solving that. So that's where that layered approach comes in. You might have redundancy built into different layers. For example, our reactive safety layer is highly redundant, but it's just within that layer. And then it's supported by these other layers that have more sophisticated responses that maybe don't need that level of redundancy because it's just either not necessary, it might just be too complex to try to do these more sophisticated compute algorithms that are actually monitoring AI in a redundant way. But there may be a little benefit, and that's why that analysis, this is why the real safety engineering is actually really complicated, and why we say, like, let us take care of it, because as roboticists, you're probably not going to hit the level of sophistication, and you're either going to be too safe or not safe enough, and it's really hard to get that balance right. And since we work with so many customers across so many different industries, we've figured out how to balance the productivity with cost and the required levels of safety.
Great. Thanks so much. Let's thank Nathan again. Thank you very much.
Thank you. Thank you.
Thank you.